There is no consensus on which power sources are best, surprisingly. Values are all over the board depending on whose publication you read. Hydroelectricity and coal power are very high, say 40-to-1 returns on your investment. Oil and gas are lower, but still very good. And nuclear and solar depend hugely on who you ask. That's why this is a job for The Rational View. The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues. Hello, and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. On this episode, I'm going to talk to you about nuclear power versus renewable energy. Now, why, you're asking, why are you pitting nuclear versus renewables? Shouldn't it be low carbon energy versus fossil fuels? And yes, it should be. I agree. The consensus of the world's leading climate scientists, as recorded in the Intergovernmental Panel on Climate Change report, or the IPCC report, as some of you may be familiar with, says that we need to cut fossil fuel emissions by about half by the year 2030 and get to net zero by 2050. And this gives us a 50% chance of towing the line on climate change. That doesn't seem good enough. The IPCC report outlines several pathways to get to net zero by 2050. And here's what they say. The only way this can be done is by ramping up both nuclear and renewables together at an unprecedented rate to displace fossil fuel burning. Now, I'm not saying we're going to stop all fossil fuels. This is going to be a gradual process, and there's a huge amount to displace. And I'm also saying we're not going to stop mining oil, because oil is the basis of the chemical industry. Oil is necessary to build plastics, to build all of our amazing chemical processes that we use in modern day society. And it's way too valuable to be burned. Burning it is just profligate waste. So why am I talking to you about nuclear versus renewables? It sounds silly. Sounds like infighting on the side of science. And we don't want that. But as I've stated before in previous podcasts, there is significant opposition to nuclear from major environmental groups. Opponents cite risks of nuclear waste or catastrophic meltdowns as making nuclear energy ineligible for consideration. Generally, they'll suggest that renewables can somehow save the day without nuclear and we will all live on rainbows and unicorn poop. It's just not true, though. Every energy source has problems. Every energy source pollutes in some way. Every energy source needs mining and materials to work. And the question is, how do you compare these things? Now, renewables have become extremely cheap to build. The production lines in China are using low-cost labor, and in Asia, they have relatively lax environmental standards. So the production of these solar panels and wind turbines has gone down in price significantly. Chinese populations near solar panel factories have risen up to protest and shut them down due to their pollution and the lakes of toxic runoff from the mining processes. No solution is perfect and without danger. The problem is that most people are unable to properly scale the risks. Most people don't have insight, and not everybody who's publicizing this stuff is being honest. Most people that are talking about them are biased in one way or another. And you listening to me are going to think that I'm biased as well. And I try not to be as a scientist, but we all bring our personal biases in this, and we have to explore our sources and be very critical of where we're getting our data. In short, this is a job for The Rational View. Now, thank you for listening to this podcast. Please share, talk about it with your friends. Please feel free to send comments to my Facebook page at Al Scott Rational. I promise to respond to all comments. Now, I've spent a lot of time researching and arguing in favor of nuclear power because of what I've uncovered so far in my learning experience. And I like to bring you all with me through this learning experience, and that's why I'm doing these podcasts, because I think it's a very important topic. But there's always more to learn in the details. And so this podcast follows on from earlier ones, and I want to give you a little bit more depth, a little bit more of an in-depth dig into the details of why or how nuclear compares to renewables, and to make sure that we can counter the propaganda that's out there from non-governmental organizations. Keep an open mind, watch for personal bias. Much of what I've learned has come from the internet. It's a great tool for researching, but you always have to go and look for the sources and look for the papers. And much of what I've learned has come from a great blog that I'd like to mention called Thoughtscapism by biologist Aida Ruishalm from Finland. Much of the other stuff that I've gleaned is from discussions on Facebook groups like the Renewables versus Nuclear discussion group. One quote from Thoughtscapism, Aida says, "We can only put risks in proper context if we compare them to the risks of avoiding those risks." And I think this is where a lot of public perception about nuclear falls down. What are the risks that people cite when discussing nuclear power? Fear of radioactive contamination from meltdowns and nuclear waste. Can we put these risks into perspective? And in a previous podcast, I spoke with radiation safety expert DJ Leclerc and tried to do that. And just as a summary, natural radiation background from the environment varies considerably across the globe from place to place. People are constantly being bombarded by radiation from space, cosmic rays that form in the shock waves from supernova remnants of stars in our galaxy and around the galaxy act as huge particle accelerators, and they fire these relativistic particles at the Earth, and they come and they shower down on us all the time, continuously, all day long. And if you can build a bubble chamber and look at these particles streaking through space, and they're coming through your body all the time. Now, the Earth is protected by magnetic fields, but it's still constantly being bombarded by these particles. The sun's ultraviolet radiation is absorbed in your skin, causing the same DNA damage that radiation from nuclear waste causes. If you get a sunburn from too much ultraviolet radiation, it's the same as the radiation burn you might get from holding plutonium in your hands. But very few of you would probably know that the increased cancer risk from getting a single sunburn is roughly on the same order as the increased cancer risk faced by the Chernobyl liquidators that were sent in to clean up. They all got 100 to 200 millisieverts, and roughly an increase in the base rate of cancer is expected on the order of like 1%. And I'll bet very few of you think about that before you go to the beach, that, oh gee, I could be getting the same amount of risk as a Chernobyl liquidator. And if you have, say, 5 sunburns, it increases your risk of skin cancer by something like 80% over the background risk. And that is in total about a 5% overall risk of getting cancer. It's roughly the same amount as what they expect an astronaut going on a round trip to Mars would have. So think about that. These comparisons people don't think about. People think, oh no, radiation from nuclear, bad. Radiation from sun, good. The rocks and soil of the Earth are naturally radioactive. Radon gas floats up from these rocks all the time, and it's a major source of radioactive exposure that people have. Our food includes radioactivity. Foods high in potassium are also high in radioactivity because a certain fraction of all the potassium in the world is radioactive, naturally. Bananas and potatoes are a significant source of our radiation. But how does one compare these sources to the risks from nuclear energy or nuclear waste? And that's a hard question to put into perspective. And these aren't the only sources of radiation. It's not just nuclear plants that have radioactive waste. The mining of rare earth elements for wind turbines and solar panels have created radioactive wastelands in China. Thorium and uranium are byproducts of this. And because nuclear plants have 64 times less material per unit power, the overall environmental impacts of mining the raw materials are about 64 times less for nuclear. You might also be surprised to find that the ash from coal plants is radioactive, and there are no restrictions on dumping it in the environment. If somehow a nuclear plant came into ownership of the coal ash from a coal plant, they would not be allowed to dump it due to the radioactivity restrictions. They would have to bury it in a stable geological repository, whereas coal plants who produce this stuff are able to spread it over the environment at will. It's a double standard, and people don't see these risks. Scientific American in 2007 stated the waste produced by coal plants is actually more radioactive than that generated by their nuclear counterparts. In fact, the fly ash emitted by a power plant, a byproduct from burning coal for electricity, carries into the surrounding environment 100 times more radiation than a nuclear power plant producing the same amount of energy. Nuclear spent fuel is stored on site in casks. It's a solid. It doesn't escape. And there's not a lot of it. There's just so much energy density in nuclear fuel that you don't need a lot of waste. But even at this level, even at the level 100 times more than nuclear energy puts into the environment, it's not noticeable compared to natural sources. The biggest risk to life from energy production is the soot in the air from fossil fuel burning that causes lung disease and premature death to millions of people every year. And that's approximate known death rate. You can calculate it. The other one, of course, is the upcoming catastrophe of climate change caused by the release of CO2 from fossil fuel burning. But let me go back and just touch on the risk from radiation catastrophes or nuclear meltdowns. The UN Scientific Committee on the Effects of Atomic Radiation, or UNSCEAR, has studied Chernobyl and Fukushima disasters, and they say that Chernobyl, best estimates, will have caused roughly 100 deaths total. Think about that. Just 100. This is supposedly the worst disaster ever to the environment. It only killed 100 people, as far as the best science can tell you. Now, Greenpeace says, no. Russia is hiding things. It's actually on the order of 100,000 deaths. Be that as it may, most scientists and people who look at the data agree that Europe's 300 largest coal plants cause about 22,000 premature deaths per year from the air pollution. So replacing them all with nuclear would still be a net health benefit, even assuming for now Greenpeace's outrageous death tally from Chernobyl, 1,000 times higher than the best science. If you had one Chernobyl disaster every 10 years, plus there would be no climate change impact. Think about that. You could have a Chernobyl every 10 years and you'd still do better than the coal plants. But what about the waste problem? And this is the fear response of most people that think about nuclear power. Well, the proper response is, what is the problem? Nobody has ever been harmed from spent nuclear fuel in and around an operational plant. It's difficult to figure out how one might be harmed by it. You'd have to go up and hug it or lick it. It's stored safely, and there's not much of it, and it's easy to contain. It's not spread around the environment like coal plant exhaust and gas plant exhaust and the mining tailings from building all of the other power plants. There are tons of toxic material associated with a lot of industrial processes. Look at those green vats that the Joker fell into. What the heck were those? It wasn't nuclear. So nuclear waste is a boogeyman, and there are solutions to it. Let's leave it at that. But let's look at the positives here. Remember what I said. If we replace all of our coal with nuclear, we're going to be saving tens of thousands of lives just in Europe every year. Globally, we're going to be saving millions of lives if we can replace fossil fuels with nuclear. And nuclear is the best solution to decarbonize our economy in the shortest time possible. Nuclear gives you isotopes for medical processes. Nuclear energy takes up such a small area of land and requires so little mining that the waste stream is orders of magnitude smaller than for renewables. The waste is all contained. It's not spewed into the environment. Think of clear skies. Think of not dying from lung cancer. The benefits of nuclear medicine have saved far more people from cancer than the risks of nuclear radiation. And again, remember that quote from Aida. The risks of not doing something are much higher than the risks of doing it. And we know what's going to happen to society if we can't decarbonize quickly. And nuclear doesn't take up much space. You don't have to cut down forests and pave over farmland to build it. It's, a very small generator can give you the same energy as hundreds of acres or thousands of acres of solar panels. I've done the math. If we were to decarbonize with renewables alone, it's going to be a bigger environmental catastrophe than the climate change. Because the availability of renewables, wind is something like 30% at best, solar in mid-latitudes is something like 10-15% at best. That means you have to overbuild your capacity by a factor of 4 to 8. So that means you have to build so much more capacity that when the sun is actually shining and the wind is blowing, you have to dump the energy and you're not getting payback. And if you want to have batteries on a grid scale that are going to last for the days when it's dark and there's no wind, well, think about the amount of lithium that you're going to have to mine to do that. That's orders of magnitude more kilowatt hours. The biggest battery out there can back up the grid for only about a minute, and you need to go to days. So yes, nuclear is extremely high energy density and renewables are low density, requiring significantly more materials and labor to build. Is this reflected in some sort of figure of merit of the energy? Well, it should be. So I went and explored what figure of merit accurately tells you how much energy you get out of the energy density of nuclear versus the energy that you have to put into something. So this is called energy return on investment, and it's a well-studied figure of merit for different energy sources. So why is EROI important? EROI, energy return on investment, measures the ratio between the energy you put in to build the power source and fuel it and the energy you get out. So it's energy out divided by the energy in. And if it's less than 1, it means you have an unsustainable drain on your resources. Your power supply requires more energy than it puts out. And in the short term, you can have the illusion of success because it is putting out energy and people aren't taking full account of the inputs into these things. It's very difficult to get a good accounting of the energy balance of different sources. And society's been lucky in having very high EROI for fossil fuels. Fossil fuel use has a high EROI. We've never had to look that closely. But now we've found that this is kind of a poison pill. The fossil fuels are killing us, and we need to stop and wean ourselves off of it. And the other alternatives are not necessarily as high. So, interestingly, there are a lot of energy sources that have EROI which are very marginal. Ethanol fuel, corn ethanol, for example, seems to be just barely feasible with an EROI estimated of 1.4. So, for every unit of energy you put in, you get 1.4 units out. And one considers all of the additional systematic adjustments that are needed to accept a new energy form into an existing grid, it's possible that many of these energy sources are going to return less energy than we put into them. And society needs something that is high in energy return, better than marginal value if we're going to thrive as an advanced society. So EROI, much larger than 1, means quick payback on your inputs, good for society. EROI less than 1 means you're actually losing energy, and the more you buy, the more it drains society. So what are the EROIs of various power sources? I'm going to get into some detail here. There is no consensus on which power sources are best, surprisingly. Values are all over the board depending on whose publication you read. Hydroelectricity and coal power are very high, say 40-1 returns on your investment. Oil and gas are lower, but still very good. And nuclear and solar depend hugely on who you ask. And that's strange, and it's because it's become a politicized issue. That's why this is a job for The Rational View. I wanted to dig into it. What is the energy return on investment for solar panels? Is it really low? Is it really high? Who's right? From what I can glean from the literature, it's somewhere between 0.8 and 4 for solar panels. So people aren't sure that integrating solar panels with the grid are actually a net benefit for society. Now, I haven't dug into this and I can't verify it, but most publications say that wind is about 16-1, coal 30-40-1, nuclear, depending on who you're asking, it could be anywhere from negative to 70-1. To sustain a modern society, you should have something like 7-1 minimum. The U.S. National Renewable Energy Lab says solar panels will pay back after only 3 years out of a 30-year lifetime. So they're suggesting it's 10 to 1. Germany, a staunchly pro-renewable country, says solar panels pay back after only 2.5 years. A recent paper by Ferroni et al., 2016, however, suggests that if you take into account the impact on the grid of renewables and their fluctuating outputs, solar panels have an energy return on investment less than 1. The Rational View needed to investigate. What's the spread from? So this is cool. I dug in. I read the papers. I read a lot of papers. I made some spreadsheets. The problem is everybody uses different units and everybody uses different comparisons. So it's a difficult comparison to make. And there's no standard method to compare and calculate the energy inputs. How far down the supply chain do you go to find the energy inputs into a source of power? Is it the mine where you get the raw material? Should you apportion it properly between different uses of the mine? What if they're mining multiple minerals? What about transportation used to move these minerals and store all the materials? Roads, road maintenance. You end up double counting if you go too deep. And you need to use a common methodology if you want to compare between different power sources. And that's the key that's not being followed right now if you look at publications from various different sources. The spread is huge. And one reason is lack of clarity on what EROI is looking at. Energy in versus energy out, or energy in versus electrical energy out, or versus electrical energy distributed to the home. Or are we looking at the societal impacts of all of the energy use in the chain? So let's compare. This is lots of fun. I looked at 3 assessments of solar panel energy return on investment. One was a pro solar power group paper by Kurland and Benson recently. They said that the EROI of solar panels is 16.6 to 1. Wow, that's amazing. We can run all of our society off of solar panels. Let's build them. But then I looked around and I found this Ferroni and Hopkirk paper of 2016. It said that the raw EROI on building solar panels is 1.6 to 1. And if you include all of the adaptations you need to use solar power on the grid, it goes down to 0.8 to 1. Wow, nobody should use solar panels. What's the right answer? So the Ferroni paper generated controversy. A guy named Rao Guy responded with a paper saying, no, you guys have made a lot of mistakes. It's actually 9 to 1. This is pretty good. 9 to 1 energy return on investment is reasonably good. It's going to pay off in a few years. In a 25-year lifetime, you're going to pay off in 2 or 3 years. So let's dig into the numbers. I had to dig in. Why are these differences? These are huge differences. And we know better, right? Someone's lying. Someone's fudging. So first I looked at the outputs. And in mid-latitudes, it depends on what you look at, but the Ferroni paper was saying 2.2 megawatt hours per square meter over the lifetime. This is what you get from a solar panel in a mid-latitude like Switzerland. And this is based on data from new Swiss solar panels. Rao Guy et al. Said, well, no, you've made some poor assumptions. We're going to project improvements in solar panels to the future in a linear progression. And so we're going to say you're going to get 2.8 megawatt hours per square meter. The paper by Kurland and Benson used a National Renewable Energy Lab's simulator and predicted 4.7 megawatt hours per square meter, so more than twice what the empirical data was showing. And so I was a little bit surprised that would be so far out. But I mean, it's idealistic. They're probably assuming the best values you can get out of laboratory panels. There's no allowance for downtime and maintenance. A lot of assumptions have to be made in these simulators that apparently did not bear out in the actual commercial panels that were tested in Switzerland. So I have some doubts about a projection as opposed to empirical data. So this isn't a huge spread, right? We're looking at a factor of 2 difference in the inputs, not going from 0.8 to 16, which is what the papers are showing. So what that means is that the inputs, the amount of energy that you assume it takes to build a solar panel, must be vastly different to get these different results. And in fact, you find that's the truth. The Ferroni paper shows that the inputs to build a solar panel are estimated at 1,300 kilowatt hours per square meter. The Raugai and Kurland papers showed values of 290 or 282 kilowatt hours per square meter, respectively. And that's huge. That's about a factor of 4 difference in the amount of energy to build a solar panel. What? We should know this better, right? The low numbers are based on a methodology published by the International Energy Agency, and they're based on energy invested as primary energy compared to a theoretical displacement of fossil energy expressed itself as primary energy. And what does that mean? I scratched my head when I heard that. What does it mean? Well, it means that these guys are giving themselves a factor of 3 benefit because they're making electricity rather than heat. And this is different from the method mandated by the Energy and Information Administration of the US or by British Petroleum or by the majority of energy analysts. And what they're doing is if the inputs to building your panels are fossil fuel heat, and you are comparing the effectiveness at making electricity, and you know that solar panels produce electricity directly, whereas nuclear plants and fossil fuel thermal generators have to suffer a factor of 3 losses creating electricity through the Carnot cycle that they use to make it. So they're dividing their inputs by a factor of 3. And that is not That is not how you calculate the energy return on investment, the raw balance of energy in versus energy out. If you're going to compare sources and look at how well they perform, then you can make this comparison. In that case, I would probably say that you would divide the efficiency of the thermal sources like nuclear and fossil fuels by 3 as their heat is wasted. And this is key. This is a key difference that is overlooked when most of these non-governmental organizations start talking about how good the energy return on investment of solar panels are. In the majority of publications that I've reviewed, and I've looked at several, the solar panel apologists are dividing their inputs by a factor of 3. So what is the impact of giving yourself a factor of 3 quality factor bonus? The energy return on investment calculated in this way no longer compares energy in versus energy out. It no longer tells you whether you get back the energy you put in. You can have a greater than 1 EROI, even though your net drain on society. Now, sure, thermal sources should be penalized by this factor when comparing electrical outputs, as I've said. But if the overall EROI is less than 1, you will always be subsidized by another energy source, and the more you build, the more of that source you will need. So if the real EROI of solar panels is less than 1, when you take all of the extended factors into account to integrate them with the grid, then the more solar panels you build, the more fossil fuels you will burn. So let's go back to the calculations and compare. If you actually make the correction and multiply back by that factor of 3, you still have a difference of 1,300 kilowatt hours versus 870 kilowatt hours. And this is still a big difference. And this is because the Ferroni paper also looked at the energy required in the chemicals that are used to produce the solar panels and the disposal of the sludge and processing of waste to dispose of these toxic chemicals. And the other papers did not look at these things. They didn't look at the embodied energy of all the materials like the metals and acids and bases and gases and cleaning agents and plastics and consumables and silicon carbide for cell slicing and nitrogen and argon and compressed air that goes into building these things. And they didn't look at transporting them to a solid waste repository. And if you do that, it adds about 50% to the total cost of materials to build your solar panel. And then you add on the faulty equipment and the hail damage. And that's just the raw EROI. Now, other people have looked at what's called extended EROI, which tries to look at the overall energy costs of using and incorporating this power. And this includes costs of labor for installation and maintenance and disposal, and updates to the grids to buffer and integrate the sources. And you may say that, no, we shouldn't be considering these things, but they are real costs. And you want to look at the overall balance of these things. For example, in Germany, which has had the Energiewende, which is trying to transform its coal and nuclear into renewables, it's got a very high level of electricity penetration, of renewable energy, intermittent renewable energy penetration. About 46% of the electricity consumed is from renewables in Germany right now. And the electrical distribution system is having difficulty with the ups and downs. You have to really overproduce at some times and underproduce at others. And back this up with gas plants currently and coal plants. The operator in Germany has to sell or dump excess energy when the wind is blowing and the sun is shining. During the year 2019, there was 211 hours where the cost of power was negative in Germany. In other words, they were paying other people to take their excess power, and it cost Germany over 100 million euros to dump their power. In February of 2020, it was so windy in Germany that the price was negative for 84 hours in a single month. And the German power consumers have to pay for this. They're asking their wind turbine owners to curtail electricity production and still paying them feed-in tariffs on their potential production. In 2015, this was 485 million euros. So this means that in the event of excessive electricity supply, when you have a lot of intermittence, the consumer has to pay for all this. And a lot of this energy is wasted if you don't have neighboring countries you can ship it to. If the whole grid starts getting like this, the energy return on investment is going to go down because no longer are you making full use of all of your power. You're dumping it. You're going to have to burn it or have good storage solutions, which are also costly in terms of energy inputs. Unless you have pumped hydro, which is a good solution, but it's geographically very limited. The situation is going to become worse in the future. This is a cost that's not included in any simple EROI calculations. And very few of the solar panel apologists will make these calculations. These are all calculated in nuclear EROI, though. Capital costs, capital interest costs, I should say, labor costs, grid costs, losses like that. So what's the upshot? The EROI of the basic energy in versus energy out equation for solar panels, Ferroni was calculating 1.6 to 1. Rao Guy, it's 3.2 to 1. And the Pro Solar Panel paper was 5.5 to 1 if you get rid of the electrical conversion bonus that they give themselves. So that means that the overall energy in versus energy out will eventually pay back. However, if you start including the extended costs of disposable of chemicals, integration with the grid, labor, the costs of the upfront capital, then you get 0.8 to 1 from Ferroni, which was the only paper that actually calculated it. And that shows that overall, the more solar you integrate with the grid, the more fossil fuels you're eventually going to have to burn. But what's the case of nuclear? It's also all over the map. Anti-nuclear non-government organizations suggest that it has a close to break-even ROI, definitely below solar panels and anything you ever see. The huge expenditures to build these plants and store the waste robs one of any possibility for quick payment in these publications. The World Nuclear Association, on the other hand, suggests that nuclear has the highest payback of any fuel at around 70 to 1. And this is looking at only thermal to thermal, so thermal inputs, thermal outputs. The question is, who's right? Now, most of the NGO literature is based on a 2005 paper by anti-nuke authors Storm, Van Leeuwen, and Smith, and they continue to put out monographs in defense of their work. The World Nuclear Analysis is also available rebutting SLS. Where do they differ? So I dug into this as well. It's easier to note where they're the same, because there's very few places. They agree on the energy associated with uranium conversion from solid to gas, and uranium fuel manufacturing energy. SLS, the Storm, Van Leeuwen, and Smith paper use numbers that are a factor of 4 higher than the World Nuclear Organization for enrichment. They use older diffusion-based technology rather than the more modern centrifuge technology, which is about an order of magnitude more efficient. Mining and milling costs of uranium assume a much lower ore content of future mines, and that makes a cost factor of about 3 to 4 difference. Operating costs are higher by SLS by a factor of 8. Decommissioning is higher by a factor of 3.5. Waste storage by a factor of 8. Nuclear waste disposal and mine remediation are not even considered by the World Nuclear Association. The biggest difference is on plant construction costs, which differ by an order of magnitude. Now, the University of Sydney came in and did an assessment of nuclear power EROI for Australia, the government, and they analyzed the differences between World Nuclear and SLS in an integrated sustainability analysis. And it turns out that they came down closer to World Nuclear than SLS in most cases, although they weren't willing to fully concede to more efficient centrifuge enrichment. The SLS mining costs are based on a model that severely penalizes the energy needed to get low ore grades and disregards the fact that uranium is a byproduct of mining other metals in a lot of cases. If the costs of SLS of mining were right, nobody would be able to afford to mine uranium. They're orders of magnitude beyond anything that an operating mine would use. And in fact, the amount of energy that they suggest is necessary to get uranium out of the ground is more than most countries can produce. So this critical oversight, when corrected, means that nuclear energy performs much better in terms of energy balance. SLS also quantify the energy requirements for restoring the mine site to greenfield conditions, which primarily involves neutralizing and immobilizing all of the mine tailings. This is never done for solar panels and the sort of rare earth elements that are going into turbines and batteries. And what about the construction cost, the order of magnitude difference between the World Nuclear Association and SLS? Well, the University of Sydney calls out SLS for using invalid methods, and they come down at 1.4 times that of World Nuclear Association in terms of their cost estimates, not 10 times. So what did University of Sydney consider their worst case? 75% availability, all diffusion enrichment, 25-year lifetime, and 0.01% ore grade. These are horrible parameters, but even then, the energy return on investment was 3 to 1. Their best case, with 100% centrifuge, 45-year lifetime, 90% availability, high-quality ores, leads to an energy return on investment of 20 to 1, a 2.5-year payback. The World Nuclear Association suggests that 40 to 60 years should be considered as the basic lifetime of nuclear, and that's all gravy in terms of the payback. One conclusion that I found from this whole exercise is that the energy intensity of nuclear energy depends critically on the grade of the uranium ore that's mined and the factor of whether or not it's the sole product of the mine. Right now, mines are tapping very large, high-quality deposits in Australia and Canada. But predictions for the future vary by orders of magnitude. Much of the world hasn't been explored. There's been bans on uranium mine exploration in most of the world. So it's very difficult to predict what the actual ore grade will be in the future. But uranium is effectively a renewable resource. It's present in seawater. It's dissolved in seawater, and it can be extracted from seawater. There are some processes that have been patented that pull it out with relatively low energy requirements. It leaches out of rocks in the seafloor, and it will never, ever be drawn down, no matter how much uranium we take out to power our civilization. So what's the upshot of all this? I dug into the energy return on investment numbers for solar and nuclear panels because I wanted to verify my assumption that nuclear, with its higher energy density and lower materials requirements, should return more energy to society than solar panels. And I wanted to get an idea of how much. And I found that in some cases, people say that it's reversed, that solar has a better energy return on investment. And I was stunned. And I dug into the numbers, and I found that the solar panel apologists were basically dividing their inputs by a factor of 3 because of the quality of the electricity that's put out directly. Instead of putting out heat, they put out electricity. So all of their EROIs are in comparison to electrical energy generators. And nuclear, not necessarily. Nuclear compares the thermal energy in to the thermal energy out. So for a 25-year lifetime on a solar panel, the actual energy return on investment is between 1.6 and 3.2. from this analysis. And the extended EROI of integrating solar panels with all of their costs with the grid looks like it's probably very close to break even. You may not be getting more energy out than you're putting in, and it may be less than 1. Looking at nuclear, the extended EROI from nuclear with a 40-year lifetime, in versus out, was calculated by University of Sydney for their analysis in Australia, and they come out to overall about 19 to 1. And this is conservative on many levels. The World Nuclear Association puts it at 60 to 1 for that lifetime. And they suggest that going to 60-year lifetime would give you a 70 to 1 return. And that's thermal in to thermal out. If you want to compare for production of electricity, the nuclear number needs to be penalized by a factor of 3 for the thermal cycle. And what that does is it brings it down to 20 to 1 from the World Nuclear Association or 7 to 1 from the University of Sydney for the extended energy return on investment. So, 7 times better to 20 times better than solar panels. So that's kind of what I was expecting. And I'm glad I was able to work through it and figure out where the differences are. But if anyone else wants to work through these numbers, you have to be careful about whether you're looking at thermal to thermal or thermal to electrical, because most of the solar panel apologists are going to be multiplying their energy returns by a factor of 3. And when you look at nuclear, they're going to be looking at all of the sort of waste treatment and mitigation and bringing all of the mining fields back to green fields. And this is not done for solar. And if you want to compare apples and apples, you got to do all the same sort of things for the mine sites that produce the materials. And it's not being done. So after all of this, I'm still very confident about my position to choose nuclear. Thanks for listening. If you're enjoying what you're hearing, please consider visiting my Patreon page and becoming a patron of this podcast at patron.podbean.com/TheRationalView.